So, on the syllabus, I said there would be 3 tests, and that the last one would be scheduled 10th week Friday. And then I also said there'd be 5 homeworks. And I just released the 4th one. So I'm debating if I should do everything, or if I should cut something, or, I know what you guys want. So I'm just trying to figure all of this out, okay? And I want to make everything a reasonable workload, okay? Let me talk a little bit about this homework 4 assignment. Okay. Oh. I have it due 1 week from today. Okay. And let's see here. So let me just talk about what it is. So the assignment, just turn something in. Even if you did absolutely nothing to it, you'll get 31 points, okay? So you won't get a 0, you'll get 31 points, okay? And then there's 2 parts, okay? Part 1 I think is easy, and that's worth 39 points. Basically, I'm asking you to comment, and then there's 13 locations in the code where I've asked you to add a comment, kind of explaining what's happening in the code. And I'm having you look at the Metropolis algorithm code for text deciphering. Okay, so you're going to go through that code. It's the code that's that I took from Andrew Landgraf's website, and I'm just having you go through it. I made a couple small modifications to it which I think improve the performance of the code, or not performance, but just how well it does the deciphering. And so there are 13 spots where I ask you to write some comments. Each comment worth 3 points. That's worth 39 points. Okay. And then, so if you just do that part, you'll get 70% on the homework, which I think is totally reasonable. And then part 2, it's the actual, what you need to do is, it's probably add maybe 10 lines of code, but it might be tough figuring out what those 10 lines of code need to be, okay? And basically, I think I posted links when we were talking about deciphering the, well, okay, before I get into part 2, are there any questions about part 1? You're just adding comments, okay? And if you do it, and I think it's relatively easy, if you do that part all correctly, even if you completely skip part 2, you'll get 70% on the homework, okay? And, I know you've got other classes, I know you've got a lot of things going on, so just weigh the, the cost and the benefit ratio, right? And so if you say, okay, part 2, I can't figure it out, I'm not gonna, just, that's fine. You turn it in, you don't get points for part 2. There's no shame in making choices and recognizing, okay? Just don't, what makes me angry is when students just like copy and paste from another student or cheat in that regard. Don't do that, okay? I've purposely made part 2 only worth 30 points out of the homework. So it's not that big of a deal, okay? What part 2 I'm having you do is I'm having you come up with a new way to calculate the probability of the deciphered text, okay? So I posted, when we were talking about MCMC for deciphering text using the Metropolis algorithm, there were, one was I linked to a textbook on ProQuest called Machine Learning for Hackers, and then the other was Andrew Landgraf's website. Now, Andrew Landgraf's website, and actually there was another document that talked about it, uses a letter-to-letter transition probability to decide whether the text is reasonable or not reasonable. Okay, so if you so transitions like TH is very high, HE very high, but transitions like J to X very low. Okay, so it evaluates the probability of the text string by looking at letter-to-letter transition probabilities. Okay. The machine learning for hackers has what it calls a lexical database, and it says, you know, the word "the" appears very frequently and has this probability. Okay. The word banana is a real word and it appears with this frequency. Okay. And then if it doesn't find a word, it says, you know, the probability of that word is practically 0. Okay. Now it's not practically 0. We give it machine epsilon, okay, which is kind of the smallest value that that we can store that and differentiate it from 0 in the thing. And so, you know, it looks at entire words and calculates the probability based on that. And so what I ask you to do is, you know, this is like the very basic idea of, you know, ensemble methods, in that we have probably the letter-to-letter transition matrix is very, very good for deciphering, because in the beginning you have all of this garbled text and you want to keep switching, you know, proposing new mappings of letters so that the text becomes less and less garbled. Okay. However, what ends up happening is that certain letter combinations, such as B, E, T, H, E, V, this will end up having a higher score than an actual word, because according to the two-letter transition matrix, you know, TH has a high score, HE has a high score, you know, ET. These are all high probability two-letter transitions. Okay, so this is a nonsense word, but it will have a higher probability score than an actual word like sporty or something like that. Okay, and so if you depend solely on the two-letter transition matrix, you might start ending up in kind of this realm. Okay, and so what we can do is we can balance that out by saying, okay, now we're going to use the lexical database, and we'll see if these are actual words or not. Okay, and so basically I've loaded up the code for the machine learning for hackers. These are the only two relevant chunks of code, really. And well, I guess let me upload these lexical.database files and stuff to CCLE. And you will use this to evaluate the probability. And so what we're going to do is you're going to basically, with the original code, with log probability, you get a score that evaluates the probability, and then this function will produce another score. And you want to basically, you can combine those two just by adding those two scores. Okay. I recommend not just doing a straight addition, but probably weight the addition of this score to be a lot lower, like 10%, 15%, or 5%, something around there. Okay, because you know, in the beginning, where all of the words are just garbage and gibberish, this is going to give it pretty much like a very large negative score. Okay, because it's just gibberish, 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 gibberish. It doesn't find any of those words in the lexical database, and so it's going to give it a very low score. Okay, and so I would recommend that you don't do a straight addition, but you combine this log probability score with you know, this log probability score in a way that you know, kind of weights them a little bit differently. And you'll use that combined log probability score to evaluate the probability of your text string. Okay, does that kind of make sense? So yeah. Yeah, way less. So basically, there's two scoring methods, right? There's log probability, which this is one function. This function uses the letter-to-letter transition matrix. Letter to letter transition probability matrix. And it gives, you know, T to H has high probability type of thing, okay? And, you know, H to E, high probability also, okay? And then the other function is log probability, what is it? Log probability of text. Okay, and this looks up the probability of each word. Probability of actual words. Okay, and what this will do is it will say, okay, the word the has high probability, but then, you know, zatka, you know, has, you know, close to 0 probability. All right, and basically I'm saying you're going to want to come up with like a combined score, which will be basically you're going to take the log probability of the text plus, and I would say a weight times log probability of text. Take this this score, okay? And my recommended weights would be something between you know, 0.05 to 15, okay, something around there, but you know, higher or lower, whatever you want, okay? And what that does is it just either emphasizes or de-emphasizes how important it is to have actual words versus reasonable letter sequences. Okay, and then so you know you would take this and then you would modify the code accordingly. All right. And you know, again, if you can't figure it out, it's okay. This part's only worth 30 points out of the entire homework assignment. I tried to think of a reasonable weight to attach to this part. But you know, if you get it, if you figure it out and you get it working, I think feels good. I would, also another suggestion is don't run everything in the R Markdown. Probably write a separate R script while you're kind of testing out your code. I think you'll just get better performance that way. Okay. All right. Questions on this? Yes.
I just had a question about the database you're using. So if it's looking at certain words and comparing the probability, how, if a word is actually a word, wouldn't the probability theoretically be 1?
It's like it came up with a probability for its occurrence in like all. I don't know where this database came from, but somehow we have this database. I got to upload it to CCLE, but somehow it has like it's gonna say like the most common word is like a, and next will be is and the, and these are like super common, and but even the word a has like a probability of like 2% or something like that. Okay, and then yeah, I don't know.
So it's not simply like a Boolean like dictionary.
No, it's not. You know, is this a real word or not? I think it has like 82,000 entries, and I think when you add them all up, it should add close to 1. So you know, everything has very small probabilities.
It's taken, like, a long time to compile that.
I don't know who did it, but it's available to us. Okay. Other questions? Yes.
So how would we know if we got it right? Would give us information exactly, or?
Yeah. How do you know if you got it? Yeah, that's the hard part. There's not a quote right, but because you're just deciphering things and it's sampling, right? So but I think what you will see is you will see improved performance. Okay, so I think the sample string is, you know, the Hamlet line, to be or not to be, and what you'll find is if you just use the regular thing, it's going to keep getting a drawing from like Hacklet and Hacklet and things like that, because those are all high probability things. But when you get, if you incorporate the actual words, then it will recognize that Hamlet and the other things will have a high probability. Okay. Okay. Is that okay? Start with part 1. Figure out what else you need to do in your life, and then if you're like, okay, I want to do this, then work on part 2. Okay. All right. I've also linked a document called Gibbs Sampling for the Uninitiated, and it's kind of a funny title. It's actually it's a really good document that that you should read through. It's 22 pages, okay, and as you read through this, a lot of times when there's a tendency, and I don't know if this is the same for you as it is for me. Sometimes if I see a giant equation, I just skip over it and I just start reading the text, hoping like, oh yeah, here's an equation. I'm sure it's correct, and I'm gonna move on. There can be a tendency to do something like that. I think with this document, try not to do that, okay? Look at each equation and make sure you understand each equation before you move on. I think the equations and the explanations that go with them are reasonable enough to understand what they mean. It does mean reading the document takes longer, okay? Because, it's very easy to read words, and it's a lot harder to read equations. But I would say take your time through the equations, and your understanding will be made stronger. Especially on for this document, which is intended to be like a tutorial, gentle introduction document. Okay, so so the first part, just let's see, maybe pages 1 through 7. Or I'll kind of review about Markov chains and kind of the Gibbs sampling algorithm that we've talked about so far. And then starting at chapter 7, the author develops what I think is a pretty cool model and application of using Gibbs sampling in a Bayesian context. All right, and so I want to further explain it in class so that when you get to that part in the document, it will, I hope, make sense, okay, as you read through. And then we'll try to build up some code here. Okay, so what we want to do, our goal is to build a document classification system. Okay. So what we're going to do is we're going to, you feed it in some, you feed it into the model, and then the model will say this is type is equal to 1 or type is equal to 0. Right now we're going to just deal with we're going to say there's only 2 classes of documents. Okay, so it could be, the document's about sports, or it's not about sports, or something like that. Okay, we're going to just start off with only 2 classes of documents, and then we can easily expand. I don't know about easily, but we can generalize to more than 2 classes if we want. Okay, so this is kind of cool already, right? Or maybe not. Maybe I was really excited about being able to, look at something of stuff and create this. Okay, so what we're going to say is we have, so each document is treated as a bag of words. Okay, so All right, and what this means is that, let's say this is my document. The document is, each document is treated as a bag of words. What we say is that, and we're going to say the bag of words is W sub j, and basically W sub j is going to be, it's going to say is appears once, and treated appears once, and the word a is once, and I should have probably alphabetized this. A as bag is, or I don't know what, each, things like this, okay? And basically you just get this kind of et cetera, et cetera, et cetera. You just get a bunch of words, and based on the words that we see. So yes, in English we have sentences, we have structures, we have paragraphs, and all of this, okay? When in our document classification, we're not going to bother with sentence structure and grammar and all of that. We're just going to say, here's a bunch of words, okay? The order of the words don't matter as long as the words, you know, if somebody else shuffled the words around, okay, it's the same document in the eyes of this system. All right, does that make sense? We're just treating it like, you can imagine a cartoon where all of the words just fell off and now it's in a bag, okay? And that's what we have. Okay, so we just treat this as, yeah, this is supposed to be you know, kind of our words here, right? Etc. All right, so this is our bag of words. And what we want to do is and we're going to say the document has a label L, and so we're going to say L sub j. So this is each document. This is document J. Document J is represented as a bag of words, W sub j. And then the document has a label, and the label L sub j is either going to be 0 or L sub j is equal to 1. Okay. And then we, in our entire system, we'll have a whole bunch of these documents. Okay, so the way we're looking at a whole bunch of documents, and so we're going to say C sub 0. This is the corpus, or all documents labeled 0. And C sub 1 would be all documents combined. Kind of, it represents all the documents together, all documents labeled 1. All right. Is this so far okay? So we've got a bunch of words, and what we want to do is we want to find what is the label given the words that we see in the document, right? So given some future document, we want to know what the label is based on the words that appear. Okay, so we want to know kind of, you know, what is the probability of L given W? And we want to, you know, ideally we wish to, we kind of want to maximize this, right? So we want to, we want the L that maximizes this value. Okay. And so with Bayes' rule, we have the probability of L given W is going to be the probability of, so we'll say for some document, it'll be the probability of the words given that label. Okay, so if we say, if we know it comes from label 0, then we have probability of certain words appearing, and we multiply this by the probability of the label itself. Okay, and then we would divide this by the probability of Wj itself. Okay, and then of course, because this is just a constant that doesn't depend on W, we can just say it's proportional to probability of W sub j given L times the probability of that. Okay, and so the label that maximizes this, the label L sub j, that maximizes probability of L given Wj is equal to argmax of L given that. Okay. Are we okay so far? Yes.
Is this like the Bayes classifier?
It is a Bayes classifier. It is a Bayes classifier, and we can treat it as a naive Bayes classifier if we just say, you know, the words are drawn independently. Okay, and that makes our life a lot easier, right? In real life, words are not drawn independently because each word you know, after a certain word, after the letter A, after the word A, only certain words are allowed, right? Like you can't have words that start with a vowel sound and things like that. So in real life, it's not truly independently drawn words, but it would be really hard to model all of the rules of the English language. So we can treat it as naive Bayes and saying the words appear independently, and we still get a good model. Okay, or I should say a useful model. Okay. Okay, we have a few. I'm gonna talk about the model that generates this thing. Okay, and so first of all, we have a beta distribution. So we're going to say the label L will come from a Bernoulli distribution. So it's either going to be a 0 or a 1. Okay, and the Bernoulli distribution requires what's the parameter there? A proportion, right? Bernoulli distribution with a proportion parameter okay, so the label basically label comes from a coin flip. With probability pi. Is that okay? Except we don't want to specify the pi ourselves. We're going to draw the pi from a distribution, a prior distribution on the coin flip parameter. Okay. So what do you think is a reasonable distribution to use to generate pi? So a beta distribution, right? The beta counts as the kind of the conjugate prior for a Bernoulli or binomial. Is that okay? So yeah, each L comes from that, and then so pi itself will come from a beta distribution. Okay, so yeah, and we can choose different parameters for this beta distribution. The beta distribution has two shape parameters, right? two shape parameters, and we're going to call these, I think gamma 1, gamma pi 1, and gamma pi 0. Right? And so yeah, if we want a uniform distribution, and if gamma pi 1 is equal to 1 and gamma pi 0 is equal to 1, then beta is uniform. Okay, but if gamma pi 1 is equal to 50 and gamma pi 0 is equal to 50, then what does our distribution look like? So our beta distribution would be uniform from 0 to 1. And then over here, if depending on what we have, then we have something centered at 0.5, right? And we can choose different values here, but so we are not specifying pi, we are specifying these what we call hyperparameters, or these parameters that define the beta distribution, and the pi will be drawn from whatever beta distribution we specify here. Okay, are we okay so far? Okay, so that's going to determine the label of our document, whether it's label 0 or label 1. Okay, so the model, this part of the illustration is we have hyperparameters gamma sub pi. This determines the value pi that we draw. The value pi determines the label of the document J. Okay, and then the label of the document J plays a role in determining the words that we see. Okay, and we're going to call this J sub k. Okay, so these are the, this is the proportion, the label, and this will be the words. Okay, so this is part of our model here. Okay, well, it's not just the label that determines the words, but there has to be a distribution on the words itself. Okay, and so to figure out how many words we get, we're going to use a multinomial distribution. Okay, you guys are familiar with the multinomial distribution? Sort of? All right, so the distribution for the words will be multinomial. Okay, so let me just, it's a expansion of the binomial. So binomial would be like how many times do you get heads versus tails? Do you get heads versus tails in 10 flips, right? If we're going to say we're going to draw 10 flips, 10 flips, how many heads versus tails do you get? Okay, multinomial would be instead of flipping a coin, you're drawing pieces of candy out of M&Ms, okay? And it's like how many red versus blue versus green versus yellow versus, I don't know, brown. I don't know what colors there are, okay? If you draw, I don't know, 40 pieces of candy. Okay, so that's how the multinomial works. And basically, so in this multinomial, we would have, so binomial requires only one proportion. You just, the proportion of getting heads, like 50%, or maybe your coin is biased, and so it's 70% heads. With the multinomial, we would have something like, okay, red appears with probability 20%, and blue appears with probability 15%, and you have a proportion or probability for each of the different categories in multinomial. Okay, basically we just have a very, very big multinomial distribution in that now we have like a selection of like 80,000 words that are possible, and we have a probability associated which each of those 80,000 words. Okay, so the multinomial, so our multinomial is basically, you know, something along, you know, 80,000 words, and each word has a probability associated with it. Okay, and so the vector of all of these, 80,000 probabilities is stored in theta. Okay, the vector of the 80,000 probabilities is stored in theta. Is that okay? And what we're saying is that based on the label of the document, the vector of probabilities changes. So for example, if we're talking about sports, okay, if the document label is sports, you know, in normal conversation, the word game and score probably has, you know, let's say, I don't know, we'll say 1 in 1,000 probability. Okay, the word game appears, I don't know, 1 in 1,000 probability. But if we're talking about sports, maybe that probability is now 1 in 300 or something like that. Okay, and so you know, the probabilities of each word changes depending on our label. Does that kind of make sense? Okay, so the vector of the 80,000 probabilities for each of the words is stored in theta, and you know, we have a theta 0 for the words that appear in documents labeled 0, and we have theta 1 for the words for label 1. Okay. Is this okay? And we don't want to specify the theta ourselves either. Okay, we do not want to specify. So just like before, we did not want to say that the label appears with has, you know, probability of 52%, or we didn't want to specify that probability. We do not want to specify the vector theta ourselves either. Okay, and just like the beta distribution, which goes from 0 to 1, is a conjugate prior for the Bernoulli. We have a conjugate prior for a multinomial, and it's called the Dirichlet distribution. Okay, and so basically, when you draw from the beta, you're going to get a value between 0 and 1, representing the probability that the coin lands heads. Okay, when you do a random draw from the Dirichlet distribution, let's say it was for this first one with the M&Ms, okay, and let's say there's 5 colors of M&Ms, maybe there's 6, okay, but you know, a random draw from the Dirichlet distribution will be a vector of 5 probabilities that add up to 1, okay, so a random draw from the beta will be a single value, and then a random draw from the Dirichlet will give you kind of the vector of 5 probabilities that you can then associate with red versus blue versus green versus yellow versus brown. Okay, so we don't want to specify the vector theta ourselves either. We draw theta from a Dirichlet distribution. Okay, and the Dirichlet distribution has its own parameters, which we will call gamma 0, okay, which has I'm sorry, gamma theta. Okay. Yes. What is a label? So this is a document classification system, right? So right now we're saying there's only two types of documents in the world, and I don't know what they are, but they're either going to be of class 0 or of class 1, okay? And the label is it class 0 or is it class 1? Okay, so that's what we have, and so so the full model illustration, we've got this determines this is the parameter for the beta, and then pi is the proportion drawn from beta. And this will determine the label j. Label j determined by coin flip. Okay. On the other hand, we have gamma theta. This is the parameter for Dirichlet. From there, we draw the vector theta. Okay, this is the vector of 80,000 probabilities drawn from the Dirichlet. Oh, let me, sorry. And this, okay, and so these two work together to decide the words that appear, okay? So we have, these are the words that appear in the document. Okay, they are drawn, so the words JK are drawn from the multinomial distribution. Defined by theta, okay? Defined by theta, and the theta is determined, which theta to use is determined by the label, L. Okay, and to show that, we often draw, these are called plates to represent that this represents our document here, okay? And okay, and we have a total of n documents total, and then each word itself is drawn randomly, okay? And there's a R here to say R sub j words in document J. Okay. So this is the model that we are setting up to show how we're going to represent the generation of the documents. Okay. So of course, in real life, this is not how documents are generated. People sit down and they type and they write words. Okay. But what we're saying, we're going to pretend we're going to have a simplified model which says, okay, first of all, we're going to flip a coin and decide whether it is document class 1 or document class 0. Okay, if it's document class 1, then the probabilities of the words are according to this vector theta, of which there's 80,000 probabilities associated with the 80,000 possible words. And then we just use a multinomial to say, okay, give me a bunch of words drawn from this giant vector, okay? And then let's say we're going to get 1,000 words drawn at random from this thing. Those are the 1,000 words that appear in our document W. Okay, so this is kind of the setup of the model. We'll talk about how we can use a Gibbs sampler to then estimate these parameters. And so I guess we'll talk about that on Friday. Okay, we'll see you then.